Okay, my name is John Obodo. We have been able to establish the electromagnetic field in earlier classes, and we consider the application of electromagnetic induction based on Faraday's law of electromagnetic induction and Lenz's law of electromagnetic induction. Here we are going to be looking at the application of electromagnetic field. So considering the earlier classes or lessons that we treated, we're able to establish some basic facts that the induced EMF in a circuit is a function of the magnetic field, the length of the conductor, the voltage, and the angle of inclination of the conductor. We also established that based on Faraday's law of electromagnetic induction, that the EMF induced is equal to minus N the flux over dt. Okay, that is for Faraday's law of electromagnetic induction. And also Lenz's law, we said that the induced EMF is equal to minus L di over dt. That is EMF induced in a coil based on the inductance of the coil, L, is dependent on the rate of change of the current and the inductance. Okay? So we have to look at the application of all these principles, all these terms that we have stated. One of them is in transformers. What is a transformer? A transformer does what the name implies. That is, it transforms voltages from one value to another, or current from one form or one value to another. Not only voltage and current, it also transforms power and frequency in a circuit. So transformers are also used in several points in power distribution, and they are also used in various places for power generation and to step down voltage or step down current. Okay, so something we'll be looking at what a transformer will do in a particular circuit. What will a transformer do and how does it function? So to see how a transformer functions, we look at a typical transformer. A transformer is of this form or nature. We have something like this. It has the primary coils and the secondary coils. The secondary coils. Okay, this is the primary side, a primary coil, and the secondary coil. Okay, so here we have the voltage at the primary, that is the VP, and the voltage at the secondary VS. Okay, we can also say that the VP is equal to the induced EMF at the primary, and also the VS is equal to the induced EMF at the secondary. So based on this is the core. The core, there is a flux around the core, the iron core. Okay, this is called the iron core. This iron core transmits the energy or voltage or current based on electromagnetic induction principle. So from Faraday's law of electromagnetic induction, we stated that the induced EMF is equal to minus N the flux over dt. Okay? And we can state that the primary EMF, that is the EMF at the primary side, is equal to number of turns at the primary, the flux over dt. Because the flux, the rate of change of the flux is constant. And at the secondary, the EMF at the secondary is equal to minus Ns, the flux over dt. So if we consider these two equations for EP and ES, we can be able to express that the primary side, the flux change is equal to the ratio of the primary EMF or voltage over number of turns at the primary. And also at the secondary, the rate of change of flux is equal to the EMF at the secondary divided by number of turns at the secondary. So since the flux change is constant throughout the coil or circuit, we can say that these two can be equated. And what we have is the primary EMF or voltage divided by the number of turns is equal to the secondary EMF of voltage divided by the number of turns at the secondary with negative. So the negative signs can cancel out. And what we have will now become what we call the equation of the transformer, which can be expressed as EP divided by ES is equal to NP all over NX. So this is what we call the transformation ratio or transformer equation. So this equation will be able to show us the type of transformer that is in play, whether it's a step-up transformer or step-down transformer. So basically, we know that there are two types of transformers, the step-up and step-down. Apart from the auto transformers and all that, the step-up transformer steps up voltage. That is, if the voltage at the input, that is at the secondary, is 12 volts, and the voltage at the secondary is 50 to 100 or 200 volts, then we are looking at step-up transformer. When the voltage at the primary is 200 volts and the voltage at the secondary is less than 200, maybe something like 100 or 120, then we talk about that as a step-down transformer. This step-up and step-down transformer is a function of the number of turns of the coils. Okay? When we look at the transformer, we look at this typical transformer. We have this, the EMF here. Number of turns here is N, NP. And number of turns here, let's say we have this. We have more turns here. So number of turns here is NS. In this case, NP is less than NS. NP is less than NS. That means in this case, we say that this transformer is stepping up voltage, because here we have the EMF at the primary and EMF at the secondary. So basically, based on what we have as transformation ratio, the EP over the ES is equal to NP over the NS. So therefore, the value of the EP at this case will be less than that of the ES. So we call this a step-up transformer. Step-up transformer. So the step-up transformer will step up the voltage or the current from the inputs to the outputs. But the step-down, let's look at that of the step-down. In the case of the step-down, we have something like this. We have step-down, we have this, and the number of turns here may be smaller. Okay? Here we have the ES, EP, and the ES. Number of turns here is NS, and number of turns here is NP. So when we consider this, the flux linking the circuit is still considered. So therefore, here, NP is greater than NS. NP is greater than NS, and EP as well will be greater than ES. So in this case, we talk about the step-down transformer. Step-down transformer. So in step-down transformer, most cases we talk about a reduced voltage or number of turns at the secondary. Okay, if we consider this type of transformer, we have the voltage or EMF at the primary to be 200 volts, and the number of turns at the primary is 10. And we are asked to look for the secondary voltage or EMF. Secondary unknown, and number of turns is given as 20. What will be the secondary EMF or voltage? So we apply the transformation ratio equation. So we have the EP over ES is equal to NP over NS. Okay, when we substitute these values, we have EP to be 200, ES unknown. We have that as unknown, and NP we have 10, and NS to be 20. So when we do some cancellations and cross multiply, our voltage at the secondary will be equal to 400 volts at the secondary, 400 volts. So we have from 200 volts to 400 volts. That means the transformer is stepping up the voltage of the supply from what we have at the primary inputs of the transformer. So considering this, we can look at other areas of the transformer. We look at what a transformer does, from power generation to consumption at our various houses. We have transformer at every point where it is needed. First of all, from the generation power plant, when the voltage is generated at 12 kV, roughly 12 kilovolts, the voltage is stepped up. It's stepped up to a very large value, up to about maybe 120 kV, from 12 to 120 kV, and it's transmitted along a transmission line. So we can also step it up to 400 kV at high voltage transmission by using a step-up transformer. So the step-up transformer will step up the 12 kV supply or generated to a 400 kilovolts at a very high frequency. Then it is transmitted through the transmission line. Then from the transmission line, it will come to a step-down transformer, or what we call a substation. At this step-down transformer, it will step it down from 400 kV to about 13 or 11 kV, maybe 13/33 kV, depending on the use. So at this point, where the transformer steps down, it is distributed to various local streets and areas. So from this case, the voltage transmitted is now getting close to the consumer. Then at each junction or street, the transformer is now located there, or is taking the voltage at 13 kV and also redistributing it again to various houses at about 240 volts supply. So that means what we have that is being consumed at our various houses, that is about 200 to 230 or 240 volts, is taken from about 12 kV at the generation power plant. But it is consumed at a very low voltage, because when you supply 12, or maybe you are supplying 12 kV to various houses, that means it will pose dangers to the human beings that are living there. Because a 12 kV voltage can fry a human being without recognition. So we can say that the voltage supply must be regulated by the transformer at each station or at each point as the voltage is being transmitted. Okay, so transformers change voltage at several points in a power distribution system. And that is why it is necessary for us to have transformers in our various locations. Okay, so that will lead us to what we call, the next one, we talk about a typical symbol for transformer. So we have a transformer as drawn earlier. We have that transformer there is a step-up transformer with a symbol. A transformer symbol is close to what we have. We have a transformer symbol as this, or we have a transformer. This is the basic symbol for transformer. So irrespective of whether it is step-up or step-down. Here is the primary side, and here is the secondary side. That is the secondary. And this is the turns. That is the turns of the coil turns of the transformer. So this is a symbol for transformer. Okay? So we can also consider how this is used when it is supplying voltages from the generation plant to the distribution point. So we have equations which I've stated earlier, that the voltage at the primary is given as Vp is equal to minus Np the flux over dt. And Vs is minus Ns the flux over dt. So by the time we consider these are the equations at the primary and the secondary point of the transformer, as stated by these equations. Okay, so when it's talk about, and that is known as transformer equation. So a typical example for us to see there, a portable X-ray unit has a step-up transformer. The 120 volt input of which is transformed to 100 kilovolts output needed by the X-ray tube. The primary has 50 loops and draws a current of 10 amps when in use. What is the number of loops in the secondary? And find the current at the secondary. So with this, we can solve for the number of loops in the secondary of the X-ray machine. So the X-ray machine also makes use of a a transformer because it steps up the voltage to a very high voltage so that S-rays can be produced. So when we consider the equation of how to generate the relationship between the voltage and the current, we consider the Lenz's law of electromagnetic induction, where we say that the EMF, induced EMF, is always such as to oppose the change produced in it. So we have the primary voltage is equal to minus L di over dt. We call this equation 1. And we have the secondary as minus L di over dt. Okay, let's assume that what we have here is current in this point, and current here is 2. So therefore, the inductance is the same. The inductance is the same. So if the inductance is the same, so we can now say that the ratio EP over ES is equal to minus L di over dt divided by minus L di over dt. This one is 1 and this is 2. Okay? So this cancels out this. And what we have left, dt, we cancel dt. We have EP is equal to, all divided by ES is equal to di1 over di2. di1 over di2. But di1 over di2 can be equal to the current. The current here, okay, I1 and the current here, I2, approximately. But we can use the power generated or power at each stage to get the value of the relation or the relation between the voltages. So in order to get that, we say, okay, the power in the transformer, which is P, is voltage times current. Okay? The power at the primary is equal to the voltage at the primary multiplied by the current at the primary. And the power at the secondary is equal to the voltage at the secondary multiplied by the current at the secondary. So since the powers are the same, the power at the primary is equal to power at the secondary. So when we consider this to be equal, then we can say that the voltage at the primary multiplied by the current at the primary is equal to the voltage at the secondary multiplied by the current at the secondary. So therefore, we have Vp over Vs is equal to Is over Ip. So we have an inverse relationship for current and voltage. Okay? Or we can also express it as Ep over Es is equal to Is over Ip. That is in terms of EMF. So we can get this in terms of EMF. Then we can also express the current in terms of the turns of the transformer. Because we know that Vp over Vs, which is equal to Ep over Es, is equal to Mp over Ns. So therefore, if we consider this and equate into this equation, what we have is Np divided by Ns is equal to Is over Ip. So with that, we can solve a relationship between current and number of turns of the coil. Peradventure, you are given that the number of turns at the primary in a circuit or in a system, electrical system, is 10, and the number of turns at the secondary is 20. Current at the primary is 15 amps. You are asked to find the current at the secondary. So we apply that relationship stating Mp over Ns is equal to Is over Ip. So when we slot in the values, Mp will give us 10 divided by Ns, 20, is equal to Is, which is unknown, divided by Ip, which is 15. So this, we cancel this, and our Is, the current at the secondary, will be equal to 15 divided by 2, and that is 7.5 ampere. That means at the secondary, the current that is flowing is 7.5, but at the primary, the current is 15 amps. That means based on the transformation ratio, the current is halved, the value. Okay? So we can consider this and look at other similar examples and solve them. Okay, So we have what we call inductance and inductors. What is inductance? Induction is a process in which an EMF is induced by changing magnetic flux. By changing what? Magnetic flux. Okay? So if we have the induction of a system as a process, we have what we call inductor. Okay? The inductor is a device that stores the magnetic field. So we have two types of induction. One of them is known as self-induction, and the other is known as mutual induction. Okay? Self-induction and mutual induction. So transformers make use of the two type of principles. So we can have a self-induction in which the current is such that it is flowing in one coil, it is being influenced by the EMF in the other coil. That is for self-induction. So we have several equations we can consider in that case. We have self-inductance and mutual inductance as explained on the slide. And if you consider how the equation is related, then we can be able to say that self and mutual induction are applicable in transformer systems. Okay, that is for that. Okay, so the self-induction, the self-inductance depends on how effective the current is increasing or creating flux. The more effective, the greater the rate of change of flux with respect to time. Okay? The self-inductance is given as the mu naught, we call this mu, n squared A-L, where this is the magnetic permeability and this is the number of turns. Then we have A as the cross-sectional area and L as the length. And this, most cases, is for a solenoid. But the solenoid is considered there is a magnetic permeability in between the coils. Okay, so in between the coils, we have magnetic permeability. Okay, for the next slide, we'll be looking at the relationship between current and voltage in terms of mutual and self-inductances. So in an inductance or in an inductor, we have inductors in series and parallel. You can arrange them in series and parallel. An inductor basically have the symbol. When you look at inductors, we have something like this, inductors. We have this, just like a coil, we have this. Then we have what we call variable inductors. Variable inductor, we have this as a variable inductor. Call this variable inductor. And this is fixed. Fixed inductors have this symbol, and variable inductors have this symbol. So you can have them in series and parallel. So when they're in series, when you have two inductors in series, two or more inductors in series, L1, L2, L3, the total inductance in the circuit. Total inductance is given as what? L. And that L is given as L1 plus L2 plus L3. That is for series connected inductors. When they're in parallel, this is for series connection. Series connection of inductors. But when we talk about the parallel connection, for parallel connection, we have inductors connected in parallel. In parallel, we have something like this. Okay? So we have 1, 2, 3. 1, 2, 3. Okay, so when they are connected in parallel, the total inductance in this circuit, which is L, is determined by using inverse. 1 over L is equal to 1 over L1 plus 1 over L2 plus 1 over L3. So this one will give us the total inductance in the circuit. Okay? So when we have three inductors in parallel, you find their reciprocals and add them. And when you have them in series, you add them just directly. Because this is based on the concept of Lenz's law of electromagnetic induction, which we stated as V is equal to L di over dt. So di over dt is always constant. And when they are direct, then we talk about the addition of the voltages as a direct form. So we have this relationship, which is used to estimate that. Okay, so that will lead us to the others. When we talk about mutual induction, we have diagram there explaining the relationship for mutual induction. That we said that the changing coil or changing field in one coil will invariably affect the currents in the other coil. That means the EMF induced in a coil will affect the current in the other coil. So when we consider this diagram, we have the voltage. The voltage in one of them is this. Okay, we have the voltage. The voltage in this, voltage in one is equal to the M1 di over dt. Di. Let's say this one is for 1. The voltage in the second one is, okay, this one is 1. This one will be 2. Okay? We have this as 2. Okay? So this is the voltage M2. We give us this. So V2 will give us M1 di2 over dt. Okay, so this is what we have. So V1 will cause a mutual induction in the other, and V2 will result to mutual induction in the first. And we have this relationship for mutual induction as a result of electromagnetic induction. So mutual induction is the property of the coil that enables it to oppose the changes in current in another coil with a change in the current of one coil. The flow changes to thus inducing EMF in the other coil. So the EMF is always induced based on the change in one. Okay, so we have an example where we talk about a 1 Henry inductor is a large inductor and very large, because we always make use of micro inductors or micro Henry inductors. So consider a device. Consider a device which have an inductance of 1, current ampere flowing through it. What happens if it tries to shut off the current rapidly, perhaps in only 1 milliseconds? An EMF given by this is induced, will oppose the change. Now, what is the magnitude of the EMF? To get the EMF, we apply the formula EMF is equal to minus L delta I over delta T. And the current in this case is, we talk about the inductance 1.0. The current changing is, we have 10 divided by 1.0 milliamps. This is the current. So at the end, what we have is 10,000 voltage. Because 1 milliseconds is same thing as a 1 times 10 raised to the power of minus 3 seconds. 1 milliseconds is 1 times 10 raised to the power of minus 3 seconds. So we know from Lenz's law, when we look at the energy stored in an inductor, from Lenz's law, that inductance oppose the change or changes in current. There's an alternative way to look at this opposition, and that is based on energy. Now, what is the energy stored in an inductor? The energy stored in an inductor depends on the inductance, the magnitude of the inductance, and the current flowing. So to get the current flowing, we consider the Lenz's law of electromagnetic induction. Then to get the energy stored in an inductor is given as this: average Li squared, where L is the inductance, and I is the current that is flowing through the inductor. So basically, the energy is measured in joules. So we can consider a case where the inductance is 5.0 Henry, okay? And the current flowing is 2.5 ampere. What is the energy due to the coil? Okay, let's say this is the current, and this is the coil. Okay, this is the coil. So how do you get the energy stored? By the coil. The energy stored will now be half Li squared, and that is half multiplied by the inductance, 5, multiplied by 2.5 squared. Okay, when we do this, we have 2.5 squared, will give us 6.25. So we have 5 multiplied by 6.25. 5 multiplied by 6.25 divided by 2. So we have 2.5 multiplied to 6.25 joules. So you can complete this, and that will give us the energy stored in the such coil. Okay. So from what we have said, that we have been able to establish that the energy stored in an inductor is a function of the inductance and the current, which you have established, and be able to solve a little problem. So you can apply it in further problems when we talk about energy in an inductor. Okay? So we look at the application of inductance and inductors. What are the applications of inductance and inductor? Basically, inductance, or the principle of inductance and inductors, are used in traffic lights. In traffic lights, I can tell when vehicles are waiting at the intersection. The inductor will be able to sense or send electrical signal that will control the light signal and allow a particular section of the road to start moving. So it's a good application in electricity. So we have exercises that we can work on based on inductance and based on transformer and electromagnetic induction. So at this point, we have been able to show you that electromagnetism, electromagnetic induction, and all that have a wide range of application in our everyday life, in our various devices and components. So with these problems or exercises, you can solve them and know how capable you can or come across other questions in physics. So have a blessed study as you go ahead with it. Okay, thank you for listening.